So in the last class we discussed about the 3-bit asynchronous counter. Okay, and also we did some logic circuit. We attached or connected some logic circuit uh, to reduce the mode of that particular counter. In that case, we have used a NAND gate for the example that we discussed. Okay, and we considered the 2-bit case ripple counter initially. Then we have considered the 4-bit case also. I think we have, yes. So we have considered 2-bit case, and we connected an AND gate externally, and that particular circuit is called as reset logic circuit. And because we have to get the value of clear equal to 1, that clear command has to be 1, so that the memory will be cleared. Okay, in that way we can reduce the mode of the counter, and we will get from that 2-bit counter, asynchronous counter, which is having 4 states. So it is mode 4 counter that can be reduced to mode 3 counter by attaching an AND gate, and through that NAND gate we had to connect the output of this 2-bit counter, and that we discussed in the last class. Okay, and we also discussed the 3-bit case. So I will add one more problem to the assignment, which is nothing but 3-bit synchronous counter. Okay, I think I hope you didn't do that. Right? Okay, so no, I think we have done that, right? So 3-bit asynchronous only we discussed it. So you add the synchronous case also with the assignment. Okay, 3-bit synchronous counter. Okay, now we will discuss what will happen if you're having 4 flip-flops. So 4-bit asynchronous counter we have to discuss. So this is just an extension to your previous section. So let us consider 4-bit asynchronous counter. Okay, so in this 4-bit asynchronous counter, how many flip-flops we need? We need 4 flip-flops, because one bit is one flip-flop can store 1 bit of data. So we need in this particular case we need 4 flip-flops. Okay, so this will result how many what will be the mode of this counter? Mode will be 2 raised to n, maximum number of states possible with this particular counter, that will be equal to 2 raised to 4, that is 16. Okay, so the numbers will be running from 0 to 15. Okay, total number of states is equal to 16, so it will be running from 0 to 15. Decimal numbers from 0 to 15. So total will be 16 states. Okay. So let us construct this particular 4-bit asynchronous counter. So if it is asking 4-bit asynchronous counter, or if it is asking, uh, for example, mode 16 asynchronous counter, both are same. Okay, so don't confuse with that. So let us construct the same here with the 4 flip-flops. We need 4 flip-flops. And we have common logic 1 for all the inputs. Common logic 1. And this. Here also we are having the same logic 1. And these flip-flops are also having same logic 1. And consider this as your J0, K0, J1, K1, J2, K2, J3, K3. Now we will be having the outputs Q0 for the first case, and that output is fetched from this first flip-flop, and which is given to the second flip-flop as the clock. We are considering the asynchronous counter, so the output of each flip-flop will be acting as the clock of the next flip-flop. This Q1, that will act as the clock for this third flip-flop, and this is Q3, sorry, Q2, and that Q2 will be acting as clock for the, and we have this Q3 here, and the output of this circuit will be taken here. So this is Q0 again. This one is Q1. This is Q2, and this one is Q3. Okay, so this is the logic 1. Now for the first flip-flop, JK flip-flop, you have to connect the clock externally. We have to connect the clock here. And for all other flip-flops, the output of the previous flip-flop will be taken as the clock. So this is a 4-bit asynchronous counter. So how this will work? So this will work, for example, initially we consider case 000. So let's consider clock here. Then we have Q0, Q1, sorry, Q here this must be Q3 because we have to consider the most significant bit in this side. Q3, Q2, Q1, Q0. So let us consider initially all the values. So here let us consider initially all the values are 0. Then we are having for the first clock edge, okay, in negative edge of that clock pulse. So in that time we are getting here we are getting 1 as for this clock pulse. Okay, so I will just put it here. That is 1. for this clock pulse. Okay, and we are having, since this is 1 and J0 K0 already, which is logic 1. So this particular first flip flop, let's say this is first flip flop 1, flip flop 2, flip flop 3, flip flop 4. And let's consider this. So in this case, the clock is 1. So, and the output Q0 will be toggled. So Q0 will become Q0. Initially, we are having Q0 value, which is equal to 0, as you can see from here. So Q0 is initially 0, but that will become 1 when the clock is 1, because the toggling will happen. So this will become 1. Okay. So it has changed from 0 to 1. And what will happen to this Q1? Q1 will be 0, because toggling will not happen for that. Q1, Q2, Q3, all these things will be 0. Why this will be 0? Because we are having a change of Q0 from 0 to 1. Okay, we are having change from 0 to 1. Okay, so which means that we are in the positive edge of the clock pulse. If you are considering the clock pulse like this, so this one is going from 0 to 1, this edge. Okay. Now, if you consider the second edge, so that will be going from here, that will be going from 1 to 0. If you consider this edge of the clock pulse, it is going from 0, sorry, it is going from 1 to 0. It's going from 1 to 0. Okay. So when we are having a transition, or the output which is going from 1 to 0, that particular transition is corresponding to the negative edge of your clock pulse. When it is going from 0 to 1, okay, that is corresponding to the positive side of your positive edge of your clock pulse. Since Q0 is in the positive edge, or Q0 is changing from 0 to 1, since Q0 is changing from 0 to 1, which means that the pulse is at the positive edge now. I'm talking about the second flip flop, case of the second flip flop. Okay. So for second flip flop, the pulse is at the positive edge when Q0 is changing from 0 to 1. So Q1 will not change. Okay, because the output is now, the second flip flop is at the positive edge, but we need negative edge of the clock pulse in order to have the toggling effect. So Q1 will be retaining its state. Q2 also will be retaining its state. Q3 also will be retaining the same state. Okay. And the clock pulse of this Q1 or the second flip flop is the Q0. As you can see from this figure, Q0 is applied as the clock pulse of the second flip flop. So this transition 0 to 1 will not change the state of the second flip flop because it is in the positive edge. Now, if you consider the next clock pulse, let's consider the second clock pulse. And in that case, we are having again 0 here. Let's consider Q0 first. Q0 again will toggle because we are applying the clock pulse, second clock pulse negative edge here. Okay. So we are having this clock here. I think I have written. Okay, that is it. So because of that clock applied at this flip flop 1, that is first flip flop, because of that, this one will become 0 for the Q0 because the toggling will happen and the Q0 value will change. Okay. Now that Q0 is changing from 1 to 0, as you can see. So this time Q0 is changing from 1 to 0, which means that for the second flip flop, the time pulse which is at the negative edge. Okay. And because of that, the second flip flop will toggle. So this 0 will be changed to 1. Okay. So now that Q1 has changed to 1, as you can see, but here we can see this 0 is changed to 1 for this Q1. Okay. So considering the third flip-flop, the time pulse is given by the output of the second flip-flop, that is Q1, and Q1 is changing from 0 to 1, which means that it is in the positive edge. It is in the positive edge of this its clock pulse, the clock pulse of the third flip-flop. So that will not change the output of the third flip-flop because it is changing from 0 to 1, which means that the clock pulse, that is nothing but Q1, is at the positive edge. Considering the third clock pulse, again we are having Q0 which will be changed from again 0 to 1 because we are applying the clock pulse that is low value, and when that negative edge comes, first flip flop will be toggled, so that will become 1. Okay, this one will become 0, will change to 1. Okay, so this time 0 to 1. 0 to 1 means positive edge of your pulse, positive edge of your clock pulse, which means that Q0 output is changing from 0 to 1. So that Q0 will be acting as the clock pulse of the second flip-flop. So that is changing from 0 to 1 means that it is in the positive edge. So since it is positive edge, we will not having any change at the flip-flop 2, and Q1 retains its states, and we will get here 1. So here there is no change in this state. The same state is it is keeping same state, so that there is no change in Q3 or the third flip flop, and there is no change because of that. There is no change in the final flip flop or the fourth flip flop. When you consider next clock pulse, this Q0 again toggles because we are applying clock pulse directly there. So this will change again to 0. This will change to 0. So now you can see it is changing from 1 to 0, which means that it is in the negative edge now. That is Q0 value which is changing, and that Q0 is at the negative edge, and that we are applying to the second flip flop. So the second flip flop is at the negative edge of that of its clock pulse. So that will toggle the second flip flop or the second flip flop's output, so that it will change from 1 to 0. And now if you consider that change, it is also giving that Q1 is at the negative edge of negative edge. Okay, which means that it is changing from high value to low value. So now Q1 is at the negative edge, okay, of that particular pulse, and then that makes or that trigger the third flip flop because it is at the negative edge, so that the third flip flop will be in the toggling state, and the Q2 value will change from 0 to 1. And now if you consider this Q2 changes from 0 to 1, so that 0 to 1 means it is in the positive edge of the clock pulse, or the change is positive side. 0 to 1 it is going, so that the flip flop 4 will not change, or output of flip flop 4 will not change, because the Q2 value which is at the positive edge. Okay, change, there is change from 0 to 1, but that is at the positive edge. So because of that, Q3 will not be changing, so that will be again 0. I hope you understood this concept. And now if you consider the next edge of the clock pulse, again Q0 will change. Q0 continuously toggle, alternatively it will toggle, and Q1, now this it is changing from 0 to 1. Q0 changing from 0 to 1, positive edge of that Q0 pulse. So since it is the Q0 pulse is at the positive edge, Q1 will not be having the clock pulse which is equal to 1, and because of that Q1 will not change, it will retain its state 0. And since it is not changing, Q1 is not changing, Q2 also will retain its states as 1. Since Q2 is not changing, or Q2 is not at the negative edge of that pulse Q2, as in because of that Q3 will not change. Now again Q0 again toggles to 0. Now it is going from 1 to 0, which means that it is at the negative edge, so that the Q1 value will change and it will toggle to 1. And since it is going from 0 to 1, it is positive clock pulse. So again Q2 value retains its state, because we are having only positive edge for the Q1, and again Q3 will be 0. Next clock pulse, we are having again toggling for Q0, that will make this 1, and we are having now we are having 0 to 1, which means that it is at the positive edge. Q0 is at the positive edge. That is applied to Q1, to the second flip flop, so that Q1 will not change, because it is the Q0 is at the positive edge. So this will retain its state 1. Again, since it is Q1 is retaining its state, Q2 also will not change, and this will be the state. And for the next clock pulse, Q0 again changes from 1 to 0. So it is changing 1 to 0, which means that it is at the negative edge of the clock pulse. And because of that, Q1 changes. Q1 again change from 1 to 0. So again, Q1 is at the negative edge of the negative edge. Okay, Q1 is also at the negative edge. So that this Q1 is given to the third flip flop. So this Q1 is at negative edge. So the third flip flop having a clock pulse which is equal to 1, so that it will trigger and toggle the state. So 1 will change to 0. Since this one is going from 1 to 0 for Q2, okay, now it is in the negative edge. Q2 is in negative edge, and that triggers the flip flop 4, fourth flip flop, and it will toggle the state Q3, and that will become 1. Now if you consider further all other values, you can directly write. You can then the next case, this will become 1. It is still in the positive edge of the pulse. So this will be 0, this will be 0, this will be 1. It retains in the same states. Again, if you go, it is going to 0. So it is in the negative edge of the clock pulse. So that Q1 will change to 1. Since 0, it is changing from 0 to 1. Q2 will not change, and Q3 also will not change. It is remaining in the same state. And then if you go further, this will be changing again. It retains Q, since it is going from 0 to 1, it is positive edge. So that Q1 retains its states, Q2 retains its states, Q3 retains its states. For the next clock pulse, it is again changing from 1 to 0. It is in the negative edge of the clock pulse, 1 to 0. So that this will change, and this will be changing, because it is again going from 1 to 0. It is in the negative edge of the negative edge, so that this will change. So again here we are having positive edge of the clock pulse, so this Q3 will not change. Now again, if you consider the next clock pulse, we are having change in Q0. Q0 toggles to 1, because since it is going from 0 to 1, it is not going to change the Q2 value, since because of that all other values will be the same. And again, you have to consider the next clock pulse, and this one will be changing to 0, 1 to 0, so that the Q2 value will toggle, and Q3, since it is going from 0 to 1, it is positive. So Q3 will be Q2 will be the same, and Q3 also will be retaining in the same position. For the next clock pulse, it will be changing from 0 to 1, so it is in the positive edge of the Q0 value. So it is positive edge of that Q0, and this will be retaining the same. So all the other values will be retaining as it is. So this is the these are the values. And if you consider the next clock pulse, what will happen? Next clock pulse, Q0 will change. Okay, Q0 will change from 1 to 0. So 1 to 0 means it is at the negative edge of Q0 value. And since it is at the negative edge, and that is given to the second flip flop, this 1 also will be toggled to 0. Okay, for the flip flop 2. And then because of this, 1 to 0 transition, that means it is at the negative edge again. So the second flip flop also provides the negative edge to the third flip flop, for as the clock pulse, so that this one is going to change to 0 again, and this will be also giving negative edge to the fourth flip flop, so that the Q3 value also will be changed or toggled to 0. So now the state, this flip flop retains its initial state, as you can see from here, this state, which is same as that what we started with. You can see here, these both states are same. So now if you this number of states, then you will be having 15 number of states. Okay, so this is a mod 15 counter, as you can see. Okay, and if you want to draw the clock pulse diagram, then you can also do that. So we need at least how many pulses we need? 16. So let's consider 16. I'm just drawing it roughly. 1, 2, 3. I don't know whether I can have 16 or not. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, let's say 17. Okay. So these are the clock pulses, and we have negative edges here. Negative edge of your clock pulse. This is your clock pulse. And initially we are considering Q0, Q1, Q2, Q3 values, which are equal to 0. I will just draw a line corresponding to these negative edges. This pulse width has to be same. In my drawing, it may not be same. So while when you draw the pulse diagram, you have to draw it as the pulse width, which is constant. Okay. So keep that in mind. In this drawings, it may not be same. It may not be looking as same, but there has to be same. The pulse is constant here. The pulse width is constant. Okay. So let us complete this one. Almost. Okay. So these are the negative edges of this clock pulse that is applied only to the first flip flop. Okay. And for the second case, we are having this. Let's take another color. Okay, let's consider Q0, Q1, Q2, Q3, Q3 different values. So first we consider Q0, then Q1, Q2, and Q3. So let us assume that initially all these values are 0. All these outputs are 0 initially. So this is 0. This one is also 0. 0. And for the first edge of the clock pulse, this Q0 changes its state until the next edge of the clock pulse, next negative edge of the clock pulse. And then when the next negative edge comes, it is going down to 0. Again, it retains its state for up to this next negative edge clock pulse of the clock pulse. Then it is going to 1. And then when the next negative edge of the clock pulse comes, it is going to 0. And this continues for all the clock pulses. This is not that much difficult to draw. you have to practice it. Otherwise, you might be in trouble when it is. And if you are drawing it for first time for the exams and all those, then it will be difficult. So you practice this drawing of this pulse diagram. So this is the Q0 states for different clock pulses. Okay. Now, if you consider the Q1 value for Q1, if you consider, so for Q1, which one is the clock pulse? Q0 output is the clock pulse. Q0 output of the Q0 is the clock pulse for Q1. So we have to consider the negative edge of the Q0 value. Okay. So for negative edge, first negative edge of the clock pulse, no, so, sorry, not the clock pulse, Q0, it will go to high. First negative edge of the Q0 value, it is going to high because this Q0 we are applied to as a clock to the next flip flop. So it will be going to 1 and it retains in the same state until the next negative edge of the Q0 value, and it will come back to 0 and again goes to 1, which means that it is stopping again at the next edge of the Q0, negative edge of the Q0 value, retains in this same state until the next negative edge of the Q0 value. So this process continues. So this will be the state variation. You can say this as your state diagram. For state diagram, we are representing in that circles. Okay, so this is also representing this state. Okay, so this is we can call this as pulse diagram. So we are having this kind of variation for Q1, and for Q2, which is the clock pulse is Q1. Q1 will be acting as the clock pulse of the the third flip flop, right? So the Q2 value will be changing when when the Q1 value is at the negative edge, which means that it is varying from 1 to 0. At that time only, the Q2 value will change. Q2 will toggle. So this will return in the 0 position until the first negative edge of the Q1 value comes, which means that when it is changing from 1 to 0 first time. So at that time, the Q2 value changes from 0 to 1, and it continues up to the next negative edge of the Q1 signal or Q1 pulse. So that is continuing again. It is continuing here, and it is going like this. And this Q2 will be acting as the clock pulse of the last or the fourth flip flop, and it will be toggling, that the Q3 value will be toggling when the negative edge of this particular Q2 value comes. Okay, so this will be going 1 at this point, and it retains in the same state until the next negative edge of this Q2 comes. It will return in the same state. So this is the pulse diagram corresponding to the 4-bit asynchronous counter or ripple counter. Okay, similarly, you can consider for the synchronous case also, for where we will be connecting the clock pulse separately to all these flip flops simultaneously. Okay, so this is how the 4-bit asynchronous counter will give you the result. You can see the states here. You can see the states from here. 0 0 0. You can see 0 0 0. Then we are having 0 0 0 1. Then 0 0 1 0. 0 0 1 1. Then 0 1 0 0. 0 1 0 1. So if you complete this, you can get different states that you have wrote here in this table. Okay, so same state you will be getting from here. 1 1 1, all those things, etc. Okay, so that's all about the 4-bit asynchronous counter. And we in the last class we discussed how we can reduce the mode of a given counter by using some external circuit, some logic gates, etc. We can by using that we can reduce the mode of a given counter. And is there any possibility to increase the mode of the counter? And that is also possible. And that particular process is called as cascading. Okay, cascading means you have to uh, arrange these counters one after another, and the output of one of the counter will be given as the input of the next. I will show that here. So cascaded counters. So cascading means we can say this. We can say counters can be here. Counters can be connected, or we can say cascaded, connected in cascade to achieve higher modulus value. And also this cascading means that implies mm, the last stage of one counter, driven or connected to or drives drives the input of next counter. So basically we are connecting for example 2 counters. In this particular case we can consider 2 counters. So if you are connecting these 2 counters, how we can connect? The output of the first counter is connected to as the input to the next counter. Okay, so in that case we can say so here also we are having what this means. Input means you are considering it as a clock. Okay, so output of the first counter will be connected as clock to the next one. Okay, that is the input. By input we mean that this is connecting as the clock. Okay, q0. I will draw that. Okay, so or you can directly write that as a clock. In this particular case it drives the input of next count. Okay, so which means that we are directly this last stage of this counter or one counter that we are considering, that drives the input of the next, which means that we are considering the last stage or the output of the one of the counter. Okay, that will be connected to the next counter, and that controls that second counter. Okay, that is the meaning of this sentence. So let us consider a 2-bit asynchronous counter that is cascaded with some 3-bit case. let's say. Okay, so assume, or let's, as an example, I can say example. Consider cascading of 2-bit and 3-bit counter. In this case, we are considering asynchronous counter. Okay, so 2-bit or 3-bit. I'll just erase this. And we are considering asynchronous counters, 2-bit and 3-bit asynchronous counter. So in this case, what you have to do is if you are considering this case, then the mode will be, what will be the mode for this 2-bit? For 2-bit mode for 2-bit case, 2-bit will be 2 raised to 2, which is nothing but 4. Okay, and mode for 3-bit, that will be equal to 2 raised to 3, which is equal to 8. Okay, so after cascading, mode of capital 1, mode of the entire counter, will be equal to, you have to take the multiplication of this. So 4 into 8, that is equal to 32. So there will be 32 state for this particular counter if you are cascading this 2-bit and 3-bit case. Okay. Now, so if you want to draw this, I'm just considering the, I'm just drawing it schematically. So I'm not going to explain the operation on all those things. So if you are having a 2-bit here and another 3-bit here, three-bit counter, I'm saying 3-bit counter and 2-bit counter, and this will be connected to a logic 1, as we know, and that is connected to this K0, and we will apply the clock pulse. We are having this clock pulse here. Okay, all the other things are here, and we are having this K0. Okay, this is your Q0, and that is given to the second flip flop as it is clocked, and this is connected to this from that common logic 1. This is logic 1, and here we are J1, K1, Q1, all those things are there. So this is your 2-bit, counter, and the output of this 2-bit counter, that is nothing but your Q1, that is connected to the next flip flop, that is in the 3-bit counter. Okay, so this part is 3-bit. This part is your 3-bit counter, and again we are having here again logic 1, and that is connected to this particular circuit, this flip flop, and here also we are having the same logic 1 connected to this one. Again we are having same logic connected to this. Okay, and you can give different values for like J2, K2, here J3, K3, and J4, K4, all those things. And we are having the similar to the previous case, we are having let's say Q2, which is connected to this particular flip flop, and if you consider Q3, that is connected to this particular flip flop, and we are having Q4, which is taken from here. So this is how we cascade two different counters and which will result in the increasing of number of state. If you are having a 2-bit mod 4 counter or 2-bit counter, then we will be having only 4 states, available states, and maximum that is possible. And if you are having 3-bit counter, then maximum number of state that is possible is 8, which means that it can run from 0 to 7, and this can run from 0 to 3 maximum. Okay. Now, if you want to increase the number of states, you can cascade these two counters, and that will produce you 32 states. Total 32 states can be produced by cascading a 2-bit and 3-bit counters, asynchronous counter in this case. Okay, so this is the process of cascading of counter. Now, if you want to do this further, then you can also consider for the case of a for example, if you need a 12 state counter, we need a 12 state. So if you consider this previous example with oh, what happens to this? It is not. I think it is not responding. Let me see whether it is. It is having some problem. This problem with my system, I think it is getting heated. Let me see that. I think something happened to this PPT. It's not showing that previous result, whatever we have wrote here. Okay, let's continue. I will write it again. If you consider that 4 variable case, means 4 what has happened to this one? Okay, now it is done. So now if you look at this previous case, as you can see from here, you can see this is equivalent to what? 0. Sorry, this is equivalent to 1, this is equivalent to 0, and this one is 2, this is 3, and so on. We can write it 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So up to 15 we can have. Again, it is going to become 0. Okay. So if you want to construct a 12 up to 12, if you need the states up to 12, decimal equivalent state up to 12, which means that binary state up to 12. So it has to count up to 12. That is up to 12 clock pulse, and then it has to go to 0. So in that case, we can construct the reset logic circuit, and we can give that clear command once this state has reached. We can give some NAND gate or something, and when this particular state comes, it has to produce the clear command equal to 1, and in such a way that we have to attach or add one more circuit along with this counter, which is nothing but reset logic circuit, and that particular circuit can make this after this particular state, the counter can go to the 0, 0, 0, 0 position, right? That we did in the last class. Okay, so that we get the initial state, so we can restrict the number of state up to 12. That is one method. Otherwise, you can directly get this you can construct this by using two different counters. Okay, for example, if you are considering a mode 4 counter, you are considering a mode 4 counter. Okay, here, if you are considering mode 4 counter, uh, mode 4 counter and a mode 3 counter. Okay, so if you are cascading these two, a mode 4 and a mode 3 counter, then what will be the number of state, total number of state, total number of states or mode of the cascaded counter? That is, so this total number of states after cascading, that is equal to mode of cascaded or cascade counter, cascade counter or cascade counter. So that will be equal to 3 into 4, right? So that is equal to 12. So we'll get 12 number of modes, same as what we discussed earlier. So if you want to get only this 12, you can do this method also. This is by cascading this mode 4 and mode 3, mode 3 and mode 4 counters, then you can restrict your number of state is equal to 12. Okay. So we can directly connect as like this. And in this particular case, we are having this is sorry, this one is mode 8, right? So this one is mode 2. So in this case, how it will come? We are having mode 2. This we already did in the last class for the mode 4 and mode 3. And first you have to check how we can connect, which Q value we had to give to which counter, that we had to consider first. Okay, so because that we have to find out whether it is the output of the 3-bit counter that we have to give to the 4-bit counter, or whether sorry, output of the mode 4 counter has to be given to the mode 3 counter, or output of the mode 3 counter has to be given to mode 4 counter. That we have to decide. That can be decided if you are looking to this particular table. We can find out that, because when you are looking into this, we are having 4 outputs here: Q0, Q1, Q2, Q3, as you can see from here. Okay, and if you consider this part 0 0 0 0 0 1 1 0 1 1. Okay, and if you consider the next part of this particular state, that is nothing but 0 0 0 0 0 0 0 0. And again you take this one, again 0 0 0 1 1 0 1 1. But here it is 0 1 0 1 0 1 0 1. Again, if you consider this up to 12, we have to consider, right? So 0 0 0 1 1 0 1 1. Here we have, oh okay, up to 11 only we have to consider, right? Not up to 12, because we are considering mode 12. So when it reaches at this point, okay, when it reaches at this point, it has to go to 0. Okay, so only up to this 11 we'll get number up to 11. So when it is reaching at this 1 1 0 0, then it has to clear all the memory, and it has to go to 0 0 0 0 position. That we did in the last class. But here we are considering a 4-bit counter and a 3-bit counter and cascade them together, and we'll get the same result, that is 12 state or mode 12, sorry, mode okay, mode 12 counter. So that we can see this first column, this one, or first box that we just draw here, that is giving me result 0 0 0 1 1 0 1 1. That is nothing but a mode 4 counter. This is nothing but a mode 4 counter. You can check that if you consider mode 4 counter, that is nothing but a 2-bit counter. Mode 4 means 2-bit. 2 raised to 2 is 4. So number of states is equal to 4. Maximum number of states is equal to 4. So this is nothing but a mode 4 counter, or this is the result of a 2-bit counter. Output of the 2-bit counter. This is nothing but the output of the 2-bit counter. This side, first one. Okay, and the next one, I will draw with another color that. So if you consider this one, that is nothing but 0, 0, 0, 0. All the values which is in this box, which is 0. Okay, for the next box, this one we consider. So this is again giving me a mode, the output of the mode 4 counter. That is 0, 0, 0, 1, 1, 0, 1, 1. But here it is changing. This one is changing, and that is, so initially this box will give me 0. That is basically it is 0, 0 state. Then it is going to change to 0, 1 state. Here also again I am getting result or output of mode 4, but here I am getting 1, 0, 1, 0, 1, 0, 1, 0. That is, I can write 1, 0 here. So what is this? What is this? 0, 0, 0, 1, 1, 0. Again, if you look, if you consider here, we are getting 1, 1, right? Here we are getting 1, 1. But in the case of mode 3, we have to get 0, 0. In the next case, we have to get 0, 0. So that we have to arrange this, and we know that this state, with these states are corresponding to mode 3 counter. These states are corresponds to mode 3 counter. And we already discussed this. These states are corresponding to mode 3 counter. So for mode 3, we already discussed this. We have connected one NAND gate to the mode 4 counter and reduced that into mode 3 counter in the last class. You can check that. So mode 3 will be having states 0, 0, 0, 1, then 1, 0. Then it is going back to the 0, 0 position. So these are the 3 state available for this mode 3 counter. And again, it will continue the same states. Okay, if you consider the other clock pulses also, then it will be continuing the same state. So this is the output of the mode 3 counter, and this one is the output of mode 4 counter, this side, this box. So from this, what we can see, this is 0, 0, 0, 1, 1, 0, 1, 1. Once it is reaching in this position 1, 1, okay, at that time it is this Q2 is getting toggled, right? When Q1 is 1, Q0 also 1, you can see here. Once this state has reached Q0 equal to Q1 equal to 1, in that particular case, this Q2 is going to become 1. Once this one is reached, that is making the toggling effect. So that is going to make the toggling of this Q2 value. Q2 value is toggled here. You can see that. Okay, Q2 value is toggled. So also we can see this Q3 does not have any effect for that. And when it comes to the second case, okay, then again this 1 is toggling to 0. Okay, that is Q2 is changing from its state 1 to 0, and this 0 is changed to 1, which means that Q3 is changing from 0 to 1. Okay, so mode 4 counter helps to toggle the mode 3 counter, or the second counter that we are connecting, that has to be mode 3. Okay, so the output of this mode 4 toggles the state of this Q2 and Q3. It is looking like that. Okay, so that we can consider that this mode 4, output of this mode 4 will be toggling this 0, 0 state to 0, 1, and then to 1, 0, which means that nothing but this part is nothing but a mode 3 counter. Okay, so mode 4 is toggling, or the output of the mode 4, which is toggling the state mode for the mode 3 counter. Okay, so we have to connect the circuit like that. in such a way that we will get the output from that that will result in this particular states. Will result in this particular state. So that we can do here also. Okay, that's how we can change or increase the number of modes with two different counters by using this cascading method. Okay. So basically in this cascading, so this mode 4 output, so first we have to consider mode 4 and then we have to consider this mode 3. Output of this mode 4 has to be connected with this mode 3 and that will allow this toggling of the states in the mode 3 counter. Okay, and that will result in the 12 states. Okay, so that is possible. So that we can get from this previous example. I hope you understood this example. From this table, we can see that one of the side which is corresponding to mode 4 result or mode 4 states, and the other one is corresponding to the mode 3 result. So we can construct a 12 state counter by cascading these two, mode 3 and mode 4, and we'll get these results. These results we can get. And the toggling will be in the mode 3 counter will be happening only once the mode 4 has all these values for one clock pulse. So if you are considering one clock pulse of this mode 4, then it has to go through all these values. Then the Q2 value will toggle, as you can see from here. Q2 value toggles to from 0 to 1. Okay, then again the mode 4 will be completing its cycle 0 0 0 1 1 0 1 1, and all these results will come. Okay, all these results will come, and then after that only the uh, mode 3 counter again toggles its states. So this time it is changing the Q3 value from 0 to 1. Okay, so we have to attach the mode 4 counter. Okay, and then to mode 3. So we have to arrange the output of mode 4 and attach that output of mode 4 to this mode 3. So in this case it is Q1 which will be attached to the Q3, sorry, Q2, that is in the mode 3. So I am not going to draw that. I hope you understood this. I will just say. So if you will be having this mode 4 here, which means that we'll be having two flip-flops. Mode 4 means two flip-flops or 2-bit counter, synchronous counter, and we'll be having the mode 3 counter here. For mode 3, we need as an additional NAND operation and all those things that we discussed in the last class. We connected this. That is the that will make that 0 0 0 0 position. As you can see, we are connecting this to this clear option. Okay, and that Q0 value is connected to this leg, and Q1. This is connected to Q1. Okay, so I think this one is Q0, right? As we explained in this table, we are looking at that one, and that one should be Q0. So this is Q0, this is Q1, and this one also went to this clear command. You can see this we already discussed in the last class. That's why I'm not going to discuss that in detail. Okay, so then we are having this JK connections with this, which is connected to the logic 1 like this. Okay, I thought I should not draw these things. Okay, anyway, so this is again logic which is connected to this two also, logic 1 gate which is connected to these two flip-flops, and only for this flip-flop we are connecting that external clock. Okay, and this one, for this one the clock is nothing but the output of the first flip-flop. and here also this Q1 has to be given to as a clock to this one. And so this is your, this one is your mode 4 counter. As you can see, this is your mode 4, and this one is your mode 3 counter. This is mode 4, this is mode 3. So if you are cascading these two, which means that if you are giving the output of your mode 4 to this, so actually this is not touching any lines here. So if you are connecting that into this mode 3 input clock pulse of this mode 3, and if you take, I think I have made one mistake here, because Q0, Q0 and Q1 is for mode 4, right? So let's just take it as, so this is Q0, let's take it like this, Q0, this is Q1, and so this is Q2, and this is Q3. So now, yes, now it is right. So this is mode 3 and this mode 4. Mode 4 is having output Q0 and Q1, and mode 3 is having output Q3, Q2 and Q3. That is same as the that table. And now if you consider this particular case and examine what is happening. So this is same. This is same as the case that we discussed as a 4-bit counter. This is same as the 4-bit counter as we discussed with the 4 flip-flops. We just discussed that. So this is same as that 4-bit asynchronous counter, but the only difference is that we are having a mode 3 counter here instead of mode 4. Even though we are having 2 flip-flops here, we are having mode 3 because we are connected a NAND gate, and which is arranged in such a way that it will stop once it reaches that binary number which is equivalent to 12. Okay, so we are connected this NAND gate in such a way that it will change its state. This Q2, Q3 value that will be changed to 0, 0 again once it reaches to that 12th position. Okay, that we did in the last class. Okay, so this is just like that 4-bit asynchronous case, but that will stop at the 12th state. Okay, so only up to 11 it will go, and then it will come back to 0, 0. So once that, as you can see, it will, it is very easy to understand. Once that reaches to this 12th state, it will be cleared. It will clear all these Q2 and Q3 values. So Q2, Q3 will become 0, 0. At the same time, what will be the values of Q1 and Q0? Q1, Q0 also will be 0, 0. Right, because it has completed its number of states like 0, 0, then it is 0, 1, 1, 0, then it is coming 1, 1, then it will go to 0, 0 again, because this is a mode 4 counter. Once it reaches, or once it is having these 4 states, then it is going to just initial state 0, 0. Okay, so at this moment 1, 1, we are having these values that we have considered as what was that? The last value that we are considering here. Let me see if it's corresponding. So the last value here, the last value that we have to consider is corresponding to that 11. You can see here the 11th. Sorry, not this one. 11 is here. So this one. So you can see this one is 1, 1, which means that it is completed all its 4th state. Mode 4 counter completed its 4th state now. So then it is going to, again, it is going to become 0, 0. At the same time, mode 3 is at this position, 1, 0 position. But since it is mode 3 counter, now you will not go to 1, 1 position. So this 1 will not come, instead of that 0, 0 will come. So the total output will become 0, 0, 0, 0. Okay, this will be the output. So which is nothing but the initial state when you are considering 12 state. Okay, so 0, 0 to 11 it will go up to 0, 0, 2, etc. Up to 11 it will go, and again it will come back to 0, 0, 0, 0, 0, 0. So this is how we can control, or we can increase the number of states by cascading two different counters. Okay, I hope you understood this. If you are having any doubt, you can ask. And now we will discuss one more counter and we will stop, which is nothing but the BCD. Okay. So in this case, we are having BCD, or we can say this is a decade triple counter. Again, this is a ripple counter, which means that it is, again, we are having an asynchronous counter here. And this time it is decade ripple counter. That is considered decade ripple counter. Oh, this you can write as only one first letter has to be capitalized. So decade, or we can say BCD also here. It's a BCD, binary coded decimal. Binary coded decimal, BCD, decade triple counter. So what is this decade means? Decade means 10. Okay, so we need actually mode 10 triple counter. This is nothing but a mode 10 counter. Decade counter means mode 10 counter, and it is a ripple counter or asynchronous counter. Okay, so this is this meaning of this decade ripple counter is mode 10 asynchronous counter, which means that we are having 10 states. We are having 10 states. Okay. Now, 10 states means what? 10 states means it has to go from 0 to 9. 0 to 9. So we have to go from 0, 0, 0, 0 to what is 9? 1, 0, 0, 1, right? In binary. So it has to go from 0, 0, 0, 0 to 1, 0, 0, 1. That is the binary equivalent of this decimal value 0 to 9. Okay. Now, if you consider the state diagram, what will be the state diagram? So the state diagram will be state diagram of this decade counter will be, you have to consider different states from 0, 0, 0, 0 to 1, 0, 0, 1. So we have initially 0, 0, 0, 0, right? And then we have 0, 0, 0, 1, 0, 0, 0, 1. Then we are having 0, 0, 1, 0, 0, 0, 1, 0, then 0, 0, 0, 0, 1, 1, right? 0, 0, 1, 1. Then here I will write 0, 0, sorry, 0, 1, 0, 1, 0, 0. Here I will be having 0, 1, 0, 1. Then again here I am having 0, 1, 1, 0, 0, 1, 1, 1. Then 1, 0, 0, 0, and again 1, 0, and 0, 0. So this is from 0, 0 to this 1, 0, 0, 1. So this is the state diagram. You can draw it much more in a better way. No problem with that. 0 1 0. So 0 1 1 1 1 0 0 0. Okay. So these are the states. I'll use some different color now. So this is the state diagram of this particular decade counter. Decade means 10. From here to this to this, here to this. It is changing the state like this. Okay. Now, if you consider the circuit diagram, how the circuit diagram will be looking like. We need up to this 101001. So we have 4 bits here. First bit is 1, second bit is 0, 0, and 1. So we need maximum 1001, which means that we need 4 bit. In other words, we need 4 flip flops. So we need 4 flip flops. 1, 2, 3, and 4. Because we are having 4 bits in our binary number, we need 4 flip flops like this, and these flip flops have to be connected. Here we have this logic 1, and that logic 1 line is going like this. That has to be connected to all the JK inputs. Here also we are having this. But also we have to connect. This is the last one. This is the value. You can consider JK flip flop or D flip flop. So we can consider D0 here, D1, D2, D3. Okay, so in this case we need only one, right? Because it is going to directly to J and K inside this D flip flop. So we have to consider only this one. I have to erase this. It's getting confused, I think. So this is the second flip flop. This is the third one. Now we are considering the D flip flop. Okay. You can also consider JK and connected in the both of these J and K inputs. No problem with that. So we are having Q0 here, Q1, Q2, Q3. Now you apply the clock pulse. So only for the first one, we have to apply the clock pulse, external clock pulse. I have to apply like this, ELK. Clock pulse ELK. And then we have to connect this Q0 to the second one, Q1 to this third flip flop, Q2 to the fourth flip flop. Now only up to this 1001 we need. Only up to 1001 we require. So we need from it has to start from 0000. Okay. Then it has to reach to the state. So I will just take it as clear here. Okay, so we need that clear option here. Here also we need clear option. So this is nothing but your clear command. Clear. You can write CLR instead of CR. I'm just writing it as here. So that is nothing but your clear command. And when you require to stop, or when you require to again go to 0, 0, so we need from 0, 0, 0, 0 to this 0, 1, 0, 0, 1. So when it reaches 1, 0, 0, 1, it will give you the 10 states, which means that 0 to 9 it will give. So once it is reaching 1, 0, 0, 1, then it has to go again to 0. So it has to go to 0. So once it reaches at this state, it has to go to 0. So this arrow is not valid because it will eliminate all other states. Anyway, so it has to be like this. Okay. So this is from 0, 0, 0, 0 to 1, 0, 0, 1. It has to go, and once it reaches at this state, it has to come back. So when it is going to 1, 0, 1, 0, this state should not be there, and when it is reaching at this state, it has to come back to this 0, 0, 0, 0 state. So in order to do that, what we had to do, q0, we already have this q0, which is 1, and q2, sorry, q1 is, so here it is q0 is equal to 1, and q1 is equal to 0, and this one is q2 is equal to 1, and here q3, which is equal to 0. And for NAND operation, that has to be 0 only when all the values which is equal to 1. So when you connect all these outputs to a NAND gate, let's say this Q3 I'm connecting to a NAND gate. You can consider any kind of NAND operation. That is not a problem. Okay. So one thing you can do is that you can connect all this output and take the output from this NAND gate. But it is a little more connections we need, since we do not require more connections in the practicals, or if you do this kind of a counter experimentally, we have to reduce the number of connections. So in order to do that, we have to make this q1 and this q3, which is equal to 1. Okay, when so this will happen when this q3 is equal to 0 and q1 is equal to 0. Both of these will be equal to 0. Our NAND gate should produce a 0, or whatever logic that you are giving to this clear input for each of these flip flops, that has to be 0 when you are reaching at this state. Okay, so at this state we are having q3 equal to 0 and q1 also equal to 0. Okay, so we can connect these two into a NAND gate. So let us take q1. Let's take q1 and q3. These two you consider, and take that, these two values you take, and give that to a NAND gate. So, and after that, this output of this NAND gate has to be applied to each of these clear command. Output of this NAND gate has to be connected to each of these clear command. So this is the only possibility that you can have when you are having q1. So I will just write all those binary values here for a better understanding. For better understanding, I will write all those values here. Okay. So we have, initially we are having 0, 0, 0, 0, then 0, 0, 0, 1, then 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, then 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, sorry, 0, 0, 1. Okay. Oh, I missed. This will be 1, 0, 0, 0, 1, 0, 0, 1, right? 1, 0, 0, 1. then 1 1, sorry, 1 0 1 0. Okay. So as you can see from here, if you look at these Q3 values and Q1 value, so this is your Q3 and this is your Q1 and this is at 11. Sorry, this is at 10, which means at 11th state number is equal to 10. Okay, so only in this state we are having Q3 equal to 0 as well as Q1 equal to 0. For all other states, if you consider, this is our initial state, yes, for initial state without that clock pulse. And if you consider all other states apart from this initial state, if you consider, then we can see that all other states we are having here, we are having Q3, which is equal to 1, even though this Q1 is equal to 0. Here we are having this, so here also it is coming Q1 and Q3. So let me see what will be the output in that particular case. So if we are applying this NAND gate to from Q3, if you are applying this NAND gate from Q3, so that this will come. So this is 0, this is 0, this is okay. So here we are having, again this also will be having 0 0, right? So I think that may not be working. So you check that whether it is coming or not. So in this case it is coming. So because 0 0, if you are applying, here we are having 0 and here also we are having 0. In that case, I think this Q2, in that case, if you are considering 0 here, Q1 and Q3 0, so this will be 0 0 here, and that has to be first AND operation that we had to do. So 0 into 0, that will be 0 0. If we could take complement of that 0 0, that will be 0, and if we take complement, that this will become 1, right? And that will be going through this clear. So clear will become 0, right? So that is not active case. It is not active case. So if you are considering 1 1, what will happen? I think this is right? This is 0. This is 0 for this case. Okay. So if you provide that into an AND gate, 0 has to be multiplied initially. So 0 dot 0 will be 0. Complement of that will be 1. That is given to this clear, then clear will be 0 state, right? So that is not right. If you are considering these two, what will happen? So 1 into 1 will come here, 1 into 1. Okay. So 1 into 1 will come, and that will produce this 0, and that will be complemented, and this will be, so, okay. So that we have to consider that 1 1. So I think I have made a mistake here. So we have to consider these two, right? Because we are having Q3. This is our Q3, and this is Q2, Q1, Q0. Oh, here I made mistake. All right. So I wrote it in the opposite way. So when we write this table, we have to write Q3 first, right? That's right. Because we have to start with the most significant bit, then to the least significant. So this, it should be like this. So in this case, Q3 will be 1. Q3 will be 1. That's why it is coming. It is not coming. So now it is okay. Okay. So now this Q3 is 1. You can see from here. I will erase this. Yeah, so 1 0 0 0. Then we will be having 1 0 0 1. With this, in this state we have to stop. So next state is 1 0 1 0. Okay. And from here, I actually wrote the Q0 Q1 positions in the reverse way. I took the reverse way. That's why it was not working. So in this case, you can see this Q3 is 1 and this Q1 is also 1. Okay. And if you put this particular, and only in this particular state, we can see that 1, 1. And if you take any other state, we are having all this Q3 value, which is equal to 0 up to this state. Okay. So that we do not have to consider any other values in this particular case, because it will give you 0 directly. And for this case, Q3 is 1, but here it is 0. Here also Q3 is 1, but here it is 0. So only this case, only this state, we are having both Q3 and Q1, which is equal to 1. So we have to consider that case, and we have taken that particular instance. So when Q3 and Q1 both are 1, in that particular case, only we will be having 1 here. Both this input to this NAND case will be equal to 1, and that will result as 0 in here. 1.1 will be 1, and complement of that will be 0, and that will be given to this clear and noted from here. That will give you 1 for this clear command, and all the values in the memory Q0, Q1, Q2, Q3 will be cleared. So that once it reaches this state, it is going to this particular state. So this state will not be there. This state will not, we cannot observe this state. Once it is reaching Q0, Q1, Q2, Q3 values reaching at this particular position, okay, these values, and then immediately that will go to the initial state 0, 0. So this state will not be there. Okay. So, so we can have this decayed ripple counter in this way by adding this NAND gate. Okay, here. If you consider any other values, you can see if you consider Q3 and Q1 values, you have all values for the Q3, which is 0 for this much of states. Okay. So if you are having a 0 in that NAND gate input here, any one of this value if equal to 0, then that will produce the output of this NAND gate is equal to 1. Okay. And that 1 will come here. If you take the dot of that or complement of that 1, that will make this clear command 0, which means that it will retain its state. Q0, Q1, Q2, Q3 will retain its states. Okay, it will not clear, it will not become clear. So only in this state we are having both the values which are equal to 1. Only in this particular state we are having Q1 and Q3 state which is equal to 1. At that moment we will be having the output of NAND gate which is equal to 0. That produce the clear command which is equal to 1 in this flip flop, in this flip flop, in all these flip flops, and that will clear the memory of each of these flip flops into 0. Okay, and we will get 0, 0, 0, 0 as the output. So this is how we can restrict this particular counter up to 10, and this particular counter is called as decayed ripple counter because we have only 10 states. And if you consider the decimal equivalence, I hope you know these values. This is 0, this is 1, this is 2, 3, 4, 4, 5, 6, 7, 8, 9, up to 9. And this decayed counter we use even in the case of this LCD, sorry, 7-segment display. If you are considering 7-segment display, how many numbers you have to show? You have to show 9 numbers. You are having 1 here, up to 9 you have to show here. So there will be 7 segments like this. So the maximum that you can get from here in this 7-segment display, how much you can get? Maximum is 9. You will not get 10. So first here it will glow. This one, this LED will glow. This will glow. This will glow. This also glows. This also glows. So you will get 9. So that is the maximum. And how much? What is the value which is the minimum in this 7-segment display? And the minimum value will be 0. Minimum value will be 0. We are having 7 LEDs or 7 segments, and then that is for minimum case. These LEDs will be glowing. This one, this one, this one, this one, this one, this one. So we will be having minimum 0 and maximum 9. That is a decayed counter that produces from 0 to this 9. Okay, and we will explain how we can do these things. If possible, we will explain that in the next class, how it is going to count and all those things. If you are using different uh, connections or number of flip flops and all those things, we will do that in the next class. So we will stop here. So in today's class, we discussed up to this decade counter, decade ripple counter, and in the assignment problem, as I said, you have to do K-map problem, two K-map problems, okay, and then that 3-bit asynchronous, 3-bit asynchronous counter, and then we are having 3-bit synchronous counter also. Complete this also. 3-bit synchronous counter. Okay, I think okay, this is enough. So you do this and submit by Friday. Okay, so let's stop here. If you're having any doubt, you can ask. Otherwise, we can